Okay, here we go. Oops. Test, 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 test. All right. Before I start, how's everybody doing? How was your 5-day weekend? Was that a pretty good deal? Yeah? It's a kind of funny thing, like it wasn't like you had a full 5 day. It'd be nice if Wednesday said, okay, no school till Monday, then you could go away. But every day you were like, am I coming back to school? So you couldn't really go for a long trip. It's kind of annoying. And most of your other classes may leak into RRR week. Would you prefer that we do that with this class? No. I think the students have spoken. For the most part, we had the lectures. We found 2 online amazing lectures from last year that were led by Bora, who my colleague in EE, who co-taught it with me, and he's actually a RISC-V expert. So it was great that he was, as a RISC-V expert, could share his data path slides. So that was data path 1 and 2, that in theory you've all seen, hopefully, because I'm going to assume you've all done that by now. So today we're just keeping up, we're keeping pace. No, were we supposed to do that? Yes, you were supposed to do that. That's part 1. Part 2 is we probably won't slide into RR week, but we probably will give extra resources. So whereas we may not have had office hours the first couple of days, we'll make sure to have a little extra office hours for that first. So we'll support you in ways, but we probably won't leak into that, into RR week too much. Yes?
Will we have review sessions during RR week?
Yeah, we'll probably have some review sessions. Yeah, we'll probably have some review sessions. They'll probably give us the room, because normally what will happen is they'll give us actually our classroom back for Monday and Wednesday, and so we may actually use those for review sessions. That'd be great.
We also have extra office hours right now.
Oh, and thank you. There's also extra hours right now for that. So, ladies and gentlemen, without further ado, welcome to CS61C Control. Woo! All right. So we are trying to build a RISC-V machine that's going to actually run the RISC-V that we were compiling and assembling and linking down to actual machine code. So let's first start with computing in the news. This is really interesting. Turns out that this clever app can detect this eye disease as much as a year ahead of clinical diagnosis. You know, all the people take pictures of the kids, but there's something about this thing called retinoblastoma or eye disorders that sometimes the pictures, it's almost like if you just scan Flickr, you could find some of these kids have these diseases, some have these conditions, and they say this app, if you use this app, you check your app, take a picture of your kid, it can diagnose this 1.3 years before the normal diagnosis of your kid. So that's amazing. If that's true, this is a nice app. It's kind of a positive spin. You always see negative spins on computing in the news, but this is a positive spin. And you see the word test, I might actually have a tablet be able to write on the slides with my pen. So we'll see if that actually works as it goes. All right. Yay, happy face, happy face. Okay, good stuff. In review, the lecture you should have seen, the 2 lectures you should have watched are Data Path 1 and Data Path 2, which describe the actual process of plugging in. By the way, Mickey's away traveling, so I'm covering this section as well. Plugging in all the logical and blocks units we built together. What do we build? An ALU, a very simple one. We built a register file made out of parallel DQ flip-flops. We built smaller single registers that can be used for staging our control pipes, our control paths. So here's the idea. We've designed a complete data path. We'll show you the picture in a second in one slide, but we'll talk about the control, how you control them. The 2 parts of building a CPU are data path, wiring these things together, going to Fry's, buying the blocks that you need, wiring them together. That's what's called the data path, the path of data. Then you control these things, turn them on and off, basically controlling the muxes and controlling things in other places. Okay, you might control the ALU to tell it what ALU operation to do, right? That kind of thing. We're going to see that we have 5 phases of execution: instruction fetch, ID, instruction decode, execute, memory access, and write back. We'll see some of this. For a lot of people, if you haven't watched those 2 lectures, this is new, so I'll go a little slower. Not all the instructions are active in all the phases. We're building a single cycle CPU. In one single cycle, it does all these things. Then we'll see how we can pipeline and make it a little faster in the next couple lectures after that. The controller specifies how to execute instructions. This is the control we're doing. This is the recap of the ISA we're getting control. There are only 47 instructions, and 37 of which are needed to run any C program. And there it is. So let's spend some time. And in theory, I can go up here and not just talk about this, but actually work on this and hope I don't drop this guy. All right. Phew. So this is complicated. If you haven't seen this before, this looks like a lot of just lines. But let's see if I can walk you through the whole process. This lower part is all the control. So everything below here, this is all your control logic. So don't worry about that for now. That's this lecture. Okay? Above this line is the data path. It starts right here. This is where the day starts. That PC is your program counter. That tells you a pointer into your memory. You have two memories, an IMEM and a DMEM. IMEM is your instruction memory. We're going to see that by separating them, I can actually access them both in one cycle. So that's useful to kind of think about that. How did I build those? Did I actually build two full memories? If I have 64 GB of RAM, do I have double 64? No. We're going to say it's an abstraction. We're going to do something called the cache. It allows me to have a small copy for IMEM and a small copy for DMEM, even though there's only really one memory. So for now, trust me in this. For now, abstract and pretend there's two memories, okay? Don't worry about it. Two memories, okay? I'll tell you that's a lie in a lecture or two. But for now, it's two memories. So the PC addresses what instruction I'm running at today. It's noon. It's 6 a.m. No, it's 12 a.m. It's the dawn of a new day. It's a new rising clock edge. Does this work? No, I lost it. It was working a second ago.
It is still working. It might not be slow.
Oh, it's nothing. It's not upsetting.
It might be slow.
It's slow. Okay. Rising edge. Come. I'll come closer. Come closer. Come on, be over here. Maybe I can just see on that thing here. This is all new. Okay, rising edge. I'm drawing on nothing. I see nothing on my screen. I'm just drawing a rising edge of a clock. Dawn of a new day. What do I do? This guy goes chunk, clock hits, turns around, grabs the current program counter, and that's what the current pointer is into memory for that instruction. Okay? So instruction memory then grabs that. That's the instruction fetch stage. Instruction fetch happens in here. God, it's really annoying. It's not even showing you. It's weird. You want to try to undo this and try to fix it? Okay. Here we go. It's not drawing anything. Okay. I'll jump here until he fixes it. Then the actual instruction. Sorry?
I'd have to do on this.
The actual instruction comes out here. Thank you so much. Comes out here. That's the 32 bits of actual instruction you've got. Okay, the actual 32 bits. That's the machine code you were compiling down. Is it a branch? Is it a jump? Is it a register-to-register operation? Those 32 bits tells you what it is. How do you start? By the opcode. The opcode tells you what that is. Okay? So now, it gets decoded into the pieces of it. Each of those fields, this is why we talked about this, each of those fields points into different places. The actual bits point into what address of A and B. I've got 5 different bits that tell me what address my register. If I'm taking register 1 plus register 2 and stuffing in register 3, this is the 5 bits of register 1. This is the 5 bits of register 2. Register 3 is this guy. So those are the bits that tell me where I'm going to do this. This is now the instruction decode. Instruction fetch, decode. I'm actually looking up what the register values are to even know what I'm doing. Oh, I'm adding R1 plus R2, putting in R3. Okay, this is where it's getting that. This is the register block. 32 bits wide, 32 bits high. The only thing that never changes is register 0. Okay, that's my register block. Does it work? Let's see. I'm drawing here in the corner. Okay.
You have to click the pen.
I have to click the pen guy. Okay, we're working it. Here we go. Pen guy. Can I go back? How do I go back? I use the clicker. Okay. I'm joking. Okay. So, it's just my hand. Come on, we're just fooling around. Here we go. So now, this register knows what I'm at. If it's a register-to-register operation, like an add, out here is the data. It's not working. It's okay. I'll do it. I'll just try it. It's not showing. Out here is the data that's coming. R of RA, whatever the 5 bits are to tell me which register it wants, that's the value in that register. And that's the value in that register. This branch comparator tells me, am I doing a branch? Is a branch equal? If that's true, then this is going to go high. If branch, this is unsigned comparison. I'm telling you, are you doing a comparison This is the branch equal line, this is the branch less than line. This is telling you if your comparison should be an unsigned or a signed comparison. These values also come around and are passed through a mux. These mux tell you which one am I taking for these inputs. Is it going to be from the register or also maybe, oh, I don't know, from the PC? So that's what this guy does, the A line. The B line says I'm going to come from the data from this register or from, what does this one come from? The immediate. Why do I use the immediate? Register plus immediate, right? Register equals register plus immediate. That's the immediate value. Get that? So this is the data path. Then I do my operation. This is the select line telling you what ALU operation I'm doing it. Am I doing an add, a subtract, a logical AND? That's doing that. This value comes out. Am I using the memory? So this is, by the way, this is called the execute stage. That's the execute stage. I can't see what I'm writing here, but I'll see if I can do it up there. Okay? So this is the instruction decode. This is the instruction fetch. That's the execute stage. Now I have a memory. Memory. What do I do in memories? What are some memory operations? Anybody remember any memory operations I have? Load word and store word. Okay? So let's think about load word. What do I do in load word? Load word. I read the memory, but also with an offset maybe. Remember that? So look, how am I using this? Load, let's follow up here. So now this might be the value of some register. This might be the offset. Remember like A of 5, A of 10? So this offset gets added to that memory access. Now, so this is the value in here was going to be your memory address. This comes in as your offset. This is set to 1. Now you're adding your base pointer plus your offset. That comes out here. That's your address. That's why that line goes into your address. That's your address. What am I writing? Well, in a store word, I'm storing from B. That comes in here as your data you're writing to. If I'm loading word, then the output comes in here as the data from memory. Gets set to this. This write back select tells you which one it wants. It's a 0. It goes all the way back. If you look at it, it goes all the way back into the data D. You put it back in there. Remember load word, load a word from memory. So this all works. All those things work. There's some extra, it's complicated because we spent 2 lectures adding more. How do you add a branch? That's why we had some PC stuff in there. All of those things are relevant. This is the working system. That's the full data path. If you just study this long enough, you can handle it and figure out what every single operation does. And please do watch those lectures if you haven't.
Then you can at least put the laser pointer on.
Oh, yeah, I could do that. Thank you. Maybe I'll put a laser pointer on. Thank you for that. And I have to click over here. Good, subtitles. Good, that's nice. I'm clicking down here. This is a whole bunch of fail, folks, a whole bunch of fail. One of the languages we use, by the way, is something called RTL. RTL stands for Register Transfer Language. Verilog is a language where you can specify how to build a system by just writing code like this. You specify what you want, and then the things just magically get built. Verilog is a pretty powerful language. So you specify what you want. So this is a way to think about what happens. For example, this got wrapped. Here's an add. Here's how this works. Here's how you specify what. By the way, in your green sheet, which you may have been looking at or maybe never looked at it yet, if you don't look at it, it'd be useful to look at it. Keep that. Let me do this and do this so that it doesn't wrap. It's silly that it wrapped. Oh, right, good. There, much better. Sorry for that. Okay, so I got an add. I've got an RD register, my destination register, an RS1, source 1, and source 2. This is what this says. R of RD gets R of RS1 plus R of RS2. This is like array notation you might have seen, right? So RS1 is a number from 0 to 31. It tells you what register to read from. And the value in that register is R of that value. All right, cool. You add them together, your ALU is set to plus. That goes back in R of RD. At the end of the day, you got to increment the PC plus 4. That's it. ORI is the same thing. The only difference is this is taken from an immediate, and you're going to use a logical OR on this guy. Jump and link. This tells you what jump and link. Oh, what does jump and link do? Look what it does. Check this out. The current PC is at a plus 4, meaning where am I coming back to after making this function call? That's where I'm going to come back to after the function call returns. That goes to R of RD, which is normally, I don't know, RA, but that's fine. then the PC gets, what am I jumping link to? Whatever is in R-1 plus this immediate, which is kind of cool. If you only want the immediate, you can put a 0 here, and this just says 0 plus immediate. So PC gets that. So I'm jumping link into the place I'm going to, and when I come back, the value would have been in R of probably RA. Okay, so this tells you what to do. Each of these is there. Look, branch, this looks like C code. This is what branch equal does. This says if these two registers are the same, I go to PC plus immediate. I offset this. This is called PC relative addressing. This is why this is PC plus immediate, PC relative addressing. Otherwise, I just go to the next operation. Just go to the next thing. I don't take the branch. That means I go to the next guy, PC plus 4. So this is all just RTL, which is really very nice. This is the big picture. So it's nice to just step back a little bit sometimes. This is the big picture. We're trying to build a processor. In the 10-mile up view, we're trying to build this guy on the left. This is what I'm trying to build. It's not even synchronized. Look at this. This is very nice. Maybe I use my hand. Maybe I'm... Yeah, I'll just drop it for now. Let's do this. We're trying to build a PC. We've been building this data path. PC is one register that keeps track of what where my current line is, my current line in my instructions. These are my 32 registers, 32 bits wide. Here's my ALU we built already. You don't know what this is yet, so ignore this cache. It just makes it a little bit faster. That's all it's doing right here, so but ignore that for now. I'm going to talk to memory. Memory is this other big block that I've built. It's 32 bits. If you think about it, 32 bits wide, you can think about it 32 bits wide. I like to think of it as 1 byte wide, and 2 to the 32 high. You can also do it as like a word wide, 4 bytes wide, and 2 to the 28 different words you can get to. You can think of it different ways. Total sum is, this is 32 bits of address. 2 to the 32 different bytes you can read and write to here. You got some I/O. We're going to see that almost the second to the last week, we'll do an I/O lecture talking about this guy. But for now, we're doing this, okay? Control talks to data path talks to control. I can ask you right now, what are these lines to here? Well, all the lines here are probably the control talk to data path. That's probably all your muxes, right? Switching. What ALU operation are you doing? That's the thing. That's where the control is talking data path. What are the lines that come back from data path to control? Let's go back to here. What are the lines that come back to data path control? Well, it's this one. I need to know actually what operation I'm doing. So you tell me the whole 32 bits of address that goes in here. That's 32 bits of your total address, so I know what to do. Oh, it's a register to register operation. Then I need to say it this way. That obviously tells you what to do. You also get data from whether these guys are equal or not. Remember this branch here? You need to know whether that's true or not, whether to do this thing. Who knows that? Well, you do. You got whether I was branch equal or branch less than, and I know from this whether I was a branch. If I'm a branch, and it says it's branch equal, and this goes high, then it is true. I was taking a branch, and they're the same. So therefore, what do I have to do? Look right here. My RTL tells me I have to do PC as PC plus immediate. Therefore, I have to switch all the controls, like this has to be plus. This better take one input from the immediate line, so this better be 1. So I'm taking from here. You get that? So it's switching all these so that it gets the PC plus immediate. This is now the new PC. It goes back, it goes back, it goes back. Oh, look. I turn this to 1. And now PC is going to get what? PC plus immediate, not just the PC plus 4. You get it? So all that's the control talking data path making it switch depending on what it's doing. So it's taking input from the lines that are coming into, 32 bits of instruction and 2 branch values based on whether your branch comparator does that, and the output is switching all this, like this is just like a little switcher, right? Up here, 1 or 0, 1 or 0, 1, 2 or 0. Okay? So it handles every single one of the RTLs I need to write. Isn't that cool? So basically, the way you built this was you went to and you wrote down all of these things of all 37 operations you needed. And then you kept adding wires and these things, and that was what those 2 lectures are doing. One by one, we kept adding it, and we started a very simple one, and we kept adding and adding and adding until we finally get to this that'll handle all the things we need. That's the idea. Is that kind of cool? Okay. So let's talk about the control logic. What the heck is that going to do? How does that even work? So here's what we start with. This is machine code, and these are the fields. This is the beauty of having a RISC-style ISA. A RISC-style ISA says simplicity is king. You want to have very rigid bars between these lines, a very standardized format. If I had to do x86 assembler, are you kidding me? They have variable length instructions. You got to be able to run programs that ran on a PC AT in 1980. Are you kidding me? How hard that is to be able to be backward compatible to all those programs in the PC world? Crazy. This is beautifully hand-engineered ISA to be as simple as it possibly can to make the hardware simple. Really rigid boundaries between these things. And as much as possible, don't move things around unless you absolutely have to. Okay, so let's see that, some of that. So that looks like, what does it look like to me? Looks like an R-type operation. Look at these bars. RS1, RS2, RD, like an add. This looks like a very common, that's not a branch, that's an R-type instruction. How did I know that? This opcode told me, and these 3 function bits told me. I can just look up on my green sheet. Oh, that's what it is. So that's how I can decide what these guys are. The opcode tells me. And the function 7 also helps you as well. All right, so here's my add. Let's do it. So here we go. Ready? Dawn of a new day. Clock goes up. The instruction for that add comes out. Now I have this instruction that's pointing to an add in here. This is just the particular pointer into memory saying, you're running instruction number 1000 somewhere. And 1000 comes in here. PC also goes into +4 so that it's ready for PC +4 in case I don't do that. It's an add, so I know I'm taking PC +4. So this is eventually going to be a 0 because I know it's going to be high. Bloop, so PC +4 comes out. This is like the delays, okay? Now I come through, I've done my instruction fetch. Now I got to do my instruction decode phase. All those lines come here. These all go hot. All these goes hot with whatever values they are. This also gets fed into my control logic. Now I can use this to make sure. At no point, by the way, did I even see it yet. So nothing I have to make a decision about yet. Meaning I was not setting any of these muxes yet. Because I just learned, just now did I see that. So just now I woke up and now I know what that is. Oh, I see, it's this kind of type. How do I know that? Well, this opcode, that function 3 and this function 7 tell me I'm doing an add between those bits. So that does that work now. PC +4. So now, bloop, I set this to be 0. By the way, I don't say 0 or 1. I actually say PC select to the actual guy I want. Like semantically, I write PC +4 here, not just 1 or 0. I have to make you look it up. It's kind of nice just to write PC +4. You know you're going to get to the next PC +4, which means I'm just going to the next instruction the next day. Here's this immediate select. Look at this. You never said before. I'm going to zoom in on this guy. What's the value to that immediate generator? This immediate generator, by the way, takes how many lines? How many lines are there? 31 to 7. That's not 32 bits. The output is 32 bits wide. Look at this, 31 to 0. That's 32 bits wide. So this guy takes immediate that isn't the full 32 bits and makes it the full 32 bits. Does it 0 extend it, like maybe a logical value? Does it sign extend it, like maybe an add, like an added add-I? It needs to know what to do. Is it a branch, doing some kind of weird thing that's doing with the branch? This tells it what to do. Why does this say, if you can zoom in on this, why does it say star? What the heck is this? It's supposed to say branch, 0 extend, or sign extend. It says star. Doesn't matter. It doesn't, just like meatballs. It just doesn't matter. Doesn't matter. Why doesn't it matter? Because it's going to be ignored. When it doesn't matter, it means it's going to come in here and it's going to go, eh. It's not going to go through here. This ALU is going to choose from there because it's doing an R to R operation, not doing it immediate. It doesn't care. So the nice thing about doesn't care is when you're actually building the gates to make it happen, if it turns out that it actually is easier to let it be 0, you can let it be 0 or 1 to have the fewest gates work out. As you're thinking about the actual logic of this, think about the logic based on if you put a lot more stars, I can get some flexibility in my Boolean massaging. Well, if it's 1, I can make it really simple. I can make it just A and B or something like that. So it's much easier. So think about stars as much as you can when you're designing these things. Reg write enable. Okay, what is this doing? The goal is to write to the register at the end of the day. So you are turning this to 1 to say, turn this on. So whatever value is on data D and address D, the next day it's going to change the register. Because your goal is to change a register with that register operation, right? It's R1 plus R2, put in R of RD. You better be changing it the next day. That's 1. Branch unsigned. Do I care what branch unsigned it is? I'm not branching. I don't care. Star. You guys get this idea? Stars are kind of cool, right? Again, branch less than. This is coming. This is not output. This is the wrong thing. This is input. This is the output. I don't know why that's there. That's a bug. This is data coming in. It shouldn't be anything there. That doesn't make any sense. It basically says ignore this. That's what it's saying. Is ignore these values. Whatever it is, I don't care about it. Which is weird on the control line, but it's fine. Okay, what am I choosing B select and A select to be? This is doing an add. Go. 0 from this data A, and this guy better come in as 0. 2 zeros. Okay. so they better be zeros. Boom, 0 and 0, because I've registered for register. What's my ALU select? What's my operation doing? Add, so that better be add. Am I writing to memory today? No, this better be read. This better not be write, so I'm not doing anything. Am I even using this? No. We're going to see that the memory is always has asynchronous reads, which means there's going to be some address here. This is actually a funny part. We should talk about this in midterm. There's a value here, which is the sum of two registers. It's not meant to be a pointer into memory. But it's coming in here. This box on reads, it's a asynchronous device, which means it's always saying, oh, here's my address. Here's what the value is at my address. So literally, this output is whatever data was at the sum of two random registers. How much money do you have in your bank? Well, $5. How much are you going to have tomorrow? $10. 5 plus 10 is 15. This is just a number, 15. But 15 is somehow being treated as an address. And memory of 15 is sitting right here on this line. Does it matter? No, why? Because it's not going to be 0. It's not sending the data from memory back to these guys. It's sending data from the ALU. So this guy better be 1, because only the ALU goes hot here. That makes sense? But it's kind of funny that this actually is reading memory and sending the output here but being ignored. Kind of fun. And that's it. That's an add. You see what this is? So all we're doing is we're going through every single operation of the 37. I'm not going to do 37 now, and we do this. We figure out what all of these have to be to make it work. The hard part was arguably wiring it up to now, but now you're going to see the hard part actually is control. It doesn't look that hard to me. Well, yeah, let me keep adding things. Still not too hard. Let me now pipeline it. Still not too hard. Oh, let me now deal with pipeline control signals. Oh, it's starting to get hard. We'll see this in a couple of lectures, why that's hard. Okay? The new PC is PC plus 4, and I'm good. That's it, I'm done. Register write is 1, which means at the end of the day, this data has come out here. Whoop, it's going through here. I should have clicked through here. This is add. This is write back of 1. Now the ALU is coming through. Now this value of R, this is the sum of the two registers coming through. This line goes hot. Bloop. And this, because this is a 1, this gets written to on the eve of the next, right before the next day that gets written to. Okay, it writes at the end of the day, basically. That cool? Question, yes?
Isn't it expensive to always be accessing memory?
That's a good question. And in fact, some folks have, I remember seeing a paper where some folks had said, you know, what we'll do is we'll basically say this address is we'll switch it so it's a 0 coming in, so it's like always 0 unless it actually uses memory, so memory can just rest. Unless it's actually using it, it's nothing from non-zero. So it's not always switching like a synchronous device, and that's a way to kind of maybe, there is some power loss when you switch things from 0s to 1s. So there was I read a paper a long time ago, I don't remember where it was, but about trying to let memory just rest when it's not being accessed. For now, we don't worry about it. We're just going to simplify it. But yes, it's a good point. Yes, question?
What are the clock inputs to the registers and the data?
Excellent. What are the clock inputs to the register and data? What do you guys think? Synchronous reads, asynchronous reads. It just reads whenever it can. Whenever the data is stable, it gets it. But synchronous writes. So I have to clock my state elements. Every state element. PCs. Registers, memory, got to clock those guys, okay? Notice this has no clock. Interesting, right? Memory is memory. That's clock because I'm writing to it. This is just reading from memory. That's treating your program as a read-only block. Not clocked. I don't change my program. It's kind of interesting, right? Okay. Clock, bloop, next day. So here's the execution. The clock goes up. Here we go. It takes a little while to go through this one, actually. I hope I can get through this here. The clock goes up. There's supposed to be a line. Okay, clock goes up. Bloop. PC. What's the PC? Now I know what the PC is. This delay between the clock rising and there. I'm now at PC 1000. That's my new pointer. That's my new program counter. Okay. Bloop. It was 1000 before, and now once I clocked, it's now sitting at 1000 afterwards. PC plus 4. This delay is. I really need to use the pen for this one. All these things point to different things. This delay between here and here, do I have a pen? No. This delay, pen, this delay is what? What's that delay right there? That's delayed through that adder. That's an adder, right? I didn't get PC plus 4 until it delayed through the adder, okay? What's this delay? That's the delay through this. That's the delay through instruction memory. It's almost like clock to queue, but for a register block. Okay? Sorry, for memory. It's whatever the memory is. This is the memory delay between when you give me a new address and when I get the outputs. Like clock to queue. I give you a new value, what's the output of an asynchronous device? Okay, next. Control logic. Well, now this has to go down to here and get passed down to here. This right here is whatever the logic is to be able to get this. I have to figure out, okay, I've got that, I've got an opcode, I got this. Now I know I'm add. So there's a delay through my logic to know that I'm an add in here. That's in here. That's the delay in here. I picked that hit there. Register of R1. That says register of RS. So this here. This is the instruction fetch. Okay, the time between. This is much faster than this. Instruction memory is usually slow if you're not in the cache. I don't want to talk about the cache. Cache makes it faster. Normally this is pretty slow. Register is really small. 32 by 32 little block of bits. That's really easy. So that's the delay here. And now this is the delay through the register block. That's this guy right here. Bloop. Same thing here. There's two registers. Obviously the same thing coming in. Now I'm reading from two values. These are the two values I'm reading from, right? I'm adding two guys and stuffing into the third. This is register of RS1, register of RS2. There's an ALU delay. Why? Well, this has to go into here. This value has to go into here, has to go through the ALU and, through the muxes, and there's an ALU processing delay. That's this guy. Only after this time, only after I start from here. From here, now I get the values. Now this is T add. This is the delay T add right here. T add, I'll put a plus here. T for plus, bloop, that's the add delay. Now I have my sum. I've got it, here it is, I've got it, let's go, we're done. We're so not done. but let's see what else we have to do. Write back. I have to now write this back to the, let's see my line, I have to write this back right here, write this back, write this back, write this back. There's my write back line, okay? This better be clean. Oh, look, there's the rising edge. This better be clean, stable at the new value before T setup, before this guy needs it. It's always T setup for this. Register 1, which is the value that is the new value of register, the output, it doesn't get written until the next rising edge of the clock. Clock to Q, now the new value goes right there. Bloop, bloop, and I'm done. And all that works. My clock is no faster than it can be. If I turn my clock a little bit faster, I might have this not stable right here before T setup, and that's the problem. We talked about that before. That's what happens when you overclock your system. You break T setups for these guys. Okay, does that make sense? That's the big picture of losing the waveforms. All right, store word. So we're going through a couple more operations. What do they all do? Ooh, what's the RTL for store word? Boy, I wish I remember the RTL for store word. You remember the RTL? Okay, memory of R of, actually I think I have it, do I have it here? I don't have it. Well, you're reading the memory from one address as the base pointer. You have some offset that's an immediate. That gets added together by this ALU. That's your location. And you're writing what value? R of RB. So this value right here gets sent out through here. So it's memory of R of RS plus the immediate. The location of the final guy, the base pointer plus the immediate, is where you put it. And what's the value? It's R of RA, of RB here. So let's do it. Clock goes high. PC plus 4. At the next operation, obviously, I'm going to do the PC plus 4. This goes in. Immediate generation. Aha! This is no longer going to be star. I care what this is. Is that a signed immediate? Is that an unsigned immediate? What kind of, how am I extending those 31 to 7 bits into the 32 bits? Signed extension, right? So I go through here, PC plus 4. Here we go. Where's my sign? S, sign extension. Good job, okay? Sign extension. Am I writing to my register at the end of the day? This is 0, 1, or star. Am I writing to my register at the end of the day? Better be 0. You almost never have write enables as stars. You need to either write or not write. You don't want to say, oh, maybe I'll write to it. Yeah, what? If you wrote to it, that's a great midterm question. If this is wrong, You are writing this value. You're writing the value. What's here? What is this line right here? This line is your address into memory, right? That's the value you would have been storing back into this data. That's not good. At whatever line this happened to be. What is this line? This 11 to 7. This is your this 11 to 7. Which register you write to happen to be some of the bits of your immediate. See how bad that would be? Those bits are the same bits. Look, 11 to 7, 31 to 7, same bits. So some bits of immediate also share in this address. Look here. Here's this. Here's your immediate. What was this used to be? Remember the add? What here? What was this? RD. Those bits are where you're going to be storing the guy. If you make this a star and it happens to make it a 1, that's what register gets overwritten. Hope it's a 0 so nothing changes. If it's not, you're in trouble. You've just overwritten a value register that shouldn't have been overwritten. This is kind of powerful, right? So you can't put that as star. That's definitely got to be a 0. All right. Do I care about my branches? No, I'm not doing a branch. So this guy is this up here. I want to sign up star here, definitely. Bloop. Star here, okay? 0 for that. All right, keep going. I do care which one this is, obviously, right? I got to care. I have to take it from R of RA. That has to be 0. This has to be from the immediate. That better be 1. This is 1 for here. This is 0 for the A. 0 and 1, so the value comes from immediate. Now it's like A of 20. A is on this line. 20 is on this line. A of 20, now I add it together. Now it's A plus 20, okay? That goes in here. Bloop, bloop, bloop. I add them together. Did the add already? Yes. Yep. Okay. And then, am I writing to memory or reading from memory or star? Never star on a right line. Circle that somewhere. Never star on a right line. Okay? I'm obviously writing. I'm store word. I'm storing it into memory. So that's a right. Right goes high. The address is sitting here. The data is sitting here. Bloop. The data comes through here. That should have gone hot right there. Right back select. Right back select. Why is this star? Why is right back select star? Where does this go? Where does this go? Look. Where does this go? Follow the right back. Where does it go? It goes into here. Am I writing to the register? No, so I don't care who's driving it. Isn't that kind of cool? Doesn't matter who puts on that line. I don't care what's on that line. I'm not using it. I'm ignoring it from the point of the register file. Okay? Blook, blook, blook. The animation's a little off, but it does all the right thing. And it clocks. And it clocks in, and when it's all done, the goal of this is clock this guy in, and that gets changed. Yay, I wrote to register. I wrote to memory. Pretty cool. Right? Branch equal. Oh, here we go. Branch equal. Same thing goes hot. This guy, branch equal. This guy, do I care about unsigned or not on a branch equal? Unsigned is only comparing less than or greater than equal. Not equal. If they're equal, I don't care. The bits better match. So it's not about unsigned versus signed. The bits better match. Okay? So that's a star on that guy. The immediate select is a branch select. This is a branch that I'm doing. Not a logical one and not a 0 extended one. Sorry, not a 0 extended, which is logical, or a sign extended. It's a branch extension. I'm not writing to my register. This is 0. I'm unsigned. This is branch equal. This is what I get. I don't know why this is 0. It should be a star. I don't think that should be a 0 on branch unsigned. But I do care about this. This is the value I care about. Based on this value, I'm going to make the choice over here of do I take the branch or not. Right there. Is my next PC +4 or from the ALU? Okay? Come through, come through, come through. I add them together. This is actually a branch comparator. So this is interesting. This branch comparator branch equal. I know why. The RTL for branch equal, if you remember from the first slide, is not just go to the immediate, it's go to R plus the immediate. That's why this is an add. That's why this matters. That's why this guy goes high. So it's R plus the immediate that goes in there. R plus the branch. So this branch goes in here, it gets there. I compare the two values, and if it's true, I'm taking the branch, it is R of RS1 plus this immediate. That comes in here, and that's why this is add. Memory write is read. That just means don't write to it. That means don't write, just treat it as read. Write back select as star because I'm not writing to this data, and that comes through here. See, I told you that line was going to go hot. The animation's a little behind here. Then this is the select. This line gets selected either 0 or 1 depending on whether that branch was equal or not. If it's 0, it's PC plus 4. If it's 1, it is PC plus R of R. It's relative. It's branches are PC relative, so which means it's branch plus PC plus. Look, PC plus. Here's the PC. Here's the PC plus this immediate, right? PC plus immediate. I don't think it's an R. It's PC plus immediate. You only have two reads. The register is from here. It's PC plus immediate. What that is. That's why it is. And so this, who knows what this is? If they're equal, it takes the top. That takes the bottom. That takes the top line. If they're not equal, it takes the bottom line. That's the idea. Okay. So there's only two register reads. Those are the registers you're comparing, and then you have the immediate of how much you add to the PC. I think we're going to skip this for now. This is a complicated thing. What's the critical path for add I? This would be a great question for you to think about. Oh, you have the yellow keys?
Yeah.
Do we have time? How many more slides? Do you have the handout today? Let's make sure I have it. Let's just do a quick sanity check. Sanity check. 10 minutes. I'm at the yellow key, which is here. We'll go back to the end. We'll do it at the end if I have time. Let me go through and we'll come back to it if I have time, okay? Okay, I didn't tell you that. Here we go. I think I did a little bit of this. I kind of already did this slowly. The PC wakes up. I instruction fetch. I go into my instruction memory to wake up to get the instruction memory. I get that value. I decode through the register. I execute through my ALU. I write to my memory, or I read from my memory in the longest case, and then I'm going to write back, which is the setup time. I write back to that register that gets it. So this is the longest path. The longest path that executes all of them, do I say it in this slide? Only in this slide. Load word makes all of these guys go hot. Load word is the longest instruction in my critical path. Look, why? I got to figure out what's my addition decode. Oh, today I'm doing a load word. What are my registers I'm reading from? Okay, load word. I'm reading from load word from some place. It's from A. What was in my A? Load it up. That's my A. A plus 20. That's my ALU works in this. I read value of A plus 20 and I store it in. I read from A of 20 and I store it in some register at the end of the day. I load from memory, put it into a register. So write back is also active. All 5 of those stages are active in, if you look at this stage, all 5 of those are active in my load word. So load word is like a pain in the butt, to be honest. It's the one that exercises all 5 stages of my pipeline and controls really how fast I can turn my single cycle CPU clock up. In this case, it's 800 picoseconds. So it's like 1 point something gigahertz. I can't go any faster than that. It's kind of a shame. It's like 4/5, 5/4, 1.25 gigahertz, right? That's as fast as I can run this particular machine. Because my load word is the guy that's exercising all these guys, and I can't do any of them at the same time so far. With all the hardware I've shown you, that's all I got. It's a little bit of a pain, but that's the longest guy. So my clock speed is 1.25. That's not that bad. Here we go. 1/800 is 1.25 gigahertz. That's not bad. Most blocks are idle, right? Like once you did your job, you're asleep. It's like, yeah, I'm kind of like a union guy. I did my thing and I'm done. I wait for the next guy. I did my job, I wait. Like my job is to do only one thing. It's all I do. If you're not going to give me work, I'm not going to do anything. So I'm locked into that. By the way, I'm pro-union, just to say. I'm just kind of making fun. Look, the smallest guy. Look at these guys. 200 picoseconds, 100, 200, 200, 200. Like literally, you remember this one time where we kind of said we pipeline slow delay combinational logic for faster clock speed? You remember that one time like this? And some people nodding their heads. look at this. I could get to 5 gigahertz if I could somehow pipeline these in a clever way. We're going to talk about that later. Okay, we'll do pipeline a whole lecture, a couple lectures on pipelining. But think about that. We're stuck at this 12.25. We could get a 4 times speed improvement if I could actually pipeline. It's pretty cool. This is the truth table. We're almost done with this control lecture. We'll actually do the clicker, I think. This is it. That's the truth table. If I summarized all the lines I cared about, here's my ad. Look, I don't care about branch equal. I don't care about less than. PC is +4 because we go to the next operation. I don't care about my immediate. I'm not using the immediate. I don't care about whether I'm unsigned my branch. I'm not using it. I do care about my A and B. They're forgotten from registers. I'm adding them together. I'm not using my memory, so I'm just reading from it passively. I am writing back to my register at the end of the day, and my write back select says, who am I writing to my back? Who am I writing back to my register? From my ALU. This is for every single operation that you see in this kind of big, I don't know, the big 13 or big 15 or something. This is it. That's the whole list. So essentially, I say, I'm building a new ISA. I write down all the operations I want to support. I write down the RTL for them. I build data path for them all. Then I analyze the data path and think about how do I have to set them all so that it all just works. And I write these all down. This all just works. Here's BEQ. All those things we just said. We did this. All these things just work. I just copied this from the thing we did before, slowly. And that's my big table. What do I do with my table now? That's the next slide. So I can either implement this big table with a ROM, and this, when I was taking this class back as an undergraduate 30 years ago, we did a ROM. Oh, I got my new EEPROM, and I would program it, I'd zap it, and now it's an EEPROM. It's just read-only memory. I have some address, I have some data. It's just like a big array that's read-only array. That's what this is. Okay? I can reprogram, which I used to do this, but I can reprogram by flashing it. It's called EEPROMs. I can add instructions to do that, to handle that. That's pretty cool. And it's when I'm kind of, when you're students level, when you're designing these things, you can actually do this. And in fact, back in the day, this is the MIT's version of this class, we got a little nerd kit with a breadboard. We wired our own computer in our 61C course. We wired our own computer and programmed the ROM to be able to actually get it to work. In fact, like, oh my God, it actually works. Hardest project I've ever done back at the time. It was really hard, but it's amazing. I got a working computer that I programmed myself in the ROMs. All these things that I told you about that you just kind of know about is there. You did it. You wired them all together. I would love to see that happen together in the future. That'd be great. I think in 150 you do some of that together, I think, right? 151, thank you, yeah. So if you want this, take 151 to get that experience. Or you could just do combinational logic circuits, right? Look, let's go here. This is just combinational logic, okay? We can just figure out what the combinational logic is. So we can do that as well. We can just work out when does this guy do a 1? Look, it does a 1 when when does this a 1? It's a 1 when it's JALR or JAL or AUPC or LW or ADI. It's like a truth table where you do sum of products with that. It's kind of cool. So this is the full data. Oh, I have time. The full data path. This is the full data path above. Today we did the control logic. How do you actually control the data path?
6 p.m.
Thank you very much. How do you control the data path? This is basic. It's funny. These are like water pipes, and these are like turning the spigots on the water pipe so the data flows the right way. That's how you should think about this. The control is what water pipe settings do you want to have the data flow the right way. You can imagine you never want to have 2 data pipes flowing to the same thing. ALUs are going to prevent, the muxes will prevent that from 2 guys from driving the same line. That's cool. Here's reg write enable for that. All right, so let me go to the clicker. Let's go to the clicker. Here we go. I got time. Here we go. Critical path. Gas, G-A-S. Gas. Yell key gas, G-A-S. Okay? Gas. yellkey.com/gas. Bloop, 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 bloop. Okay. What is the critical path for add-I? Can you see this on your slides? Should I turn the lights up to see your slides better? If you can't see your slides and you don't want to be squinting, get some eye strain. Hope does that help a little bit? It's a little dark. All right. We still have time. Let me see, yeldkey.com/gas. Okay, let's go there. yeldkey.com/gas. Whoops. yeldkey.com/gas. Oh, edit. I can edit this. And I can also see responses for this. Hey, here we go. And whoa! Boy, look at this. Okay, you're very strong on the 3, which, is that 2? You like 2 a lot. Okay. All right. Let's go back to this. Let's work it through. Okay. How does this work? Okay, dawn of a new day. What's the first thing I see? Clock to queue. Clock to queue on the PC, right? Clock to queue. I pay that price, any one of them. What's the next thing? Instruction fetch, right? So IMEM, TIMEM. Then what does it do? This is on a what? This is an add I. So now what happens next? I think I actually have it here. This is what register to read. This is your immediate gets extended, right? It's an add I. Your I is not 32 bits wide, so it has to be extended. So look, it's the max of the register or the immediate, whichever here takes longer, right? Plus, there's a mux, there's an ALU, there's the max, there's my ALU, there's one of the muxes here, and then here's another mux right here in the spotlight, 2 muxes, mux number 1, mux number 2, and you're all done, T setup for this guy. So, number 2, okay? But the key thing that was hard was it's the slower of these 2 paths between the register file or the immediate extender, okay? Signed extender. That's it. Good job, folks. Number 2, well done. We'll see you again on Wednesday. Woo! Thanks, everybody. Hey.
For this Yelky question,
Yeah.
if